Okay, let's dive right into this. We all live our lives moving through space and time, right? We think of them as the fundamental background of, well, everything. But what if I told you that's all just an illusion? We're going to explore a truly radical idea from the absolute frontiers of physics, one that suggests space-time itself isn't real, but actually emerges from something much, much stranger. So let's just get to the big question right away. Is our universe a hologram? Now I know, that sounds like something straight out of science fiction, but it's a very serious question that physicists are wrestling with right now. The basic idea is that this three-dimensional world we all experience might just be a projection, something encoded on a distant two-dimensional surface. And this really gets to the heart of it. Some of the smartest people on the planet are starting to believe that space and time are not the ultimate building blocks of the universe. Instead, they might be what we call emergent properties. Think of it like this. The wetness of water, right? That property comes from trillions of H2O molecules interacting. A single molecule itself isn't wet. So, to really understand why scientists are even considering something this wild, we need to talk about the biggest, most fundamental conflict in all of modern physics. Here's the deal. We have two theories that are just spectacularly good at what they do. On one hand, you have general relativity, which is Einstein's masterpiece. It describes the big stuff, planets, stars, galaxies, and it tells us that spacetime is this smooth, beautiful, curving fabric. Then, on the other hand, you have quantum mechanics. It's our guide to the super small, atoms, particles, where everything is weird, grainy, and based on probability. The problem? They are completely, fundamentally incompatible. When you try to make them work together, the math just shatters. And this isn't just some abstract headache. I mean, listen to how MIT physicist Daniel Harlow puts it. When you try to describe a place where both theories have to be true, like inside a black hole, he says, we get equations that don't seem to make very much sense. For decades, this has been a gigantic roadblock, stopping us from getting to a real theory of everything. But now, a totally new clue has popped up, suggesting a way around this roadblock. And it's that crazy idea we started with. What if space-time isn't fundamental at all? This is that concept of emergence again. Let's go back to the water analogy, because it's perfect. One H2O molecule by itself isn't liquid, it doesn't have a temperature. But you get a bajillion of them together, and those properties just emerge from how they all interact with each other. The theory is that spacetime could be exactly like that. A huge, large-scale effect built from countless tiny quantum interactions. So, what are these quantum interactions? Well, a fascinating idea, summed up by this deceptively simple equation, ER equals EPR, suggests a direct and, frankly, a pretty shocking link between the world of geometry and the world of quantum mechanics. Let's break that down. The EPR part is all about quantum entanglement. You've probably heard of it. Einstein called it spooky action at a distance. It's this bizarre phenomenon where two particles can be linked, and I mean linked, so that if you measure one, you instantly know the state of the other, even if it's on the other side of the galaxy. It's a cornerstone of quantum physics. Now for the ER side. This stands for Einstein-Rosen bridges, but you probably know them by a much cooler name, wormholes. These are these theoretical tunnels through the fabric of space-time, a really weird prediction that comes straight out of Einstein's theory of general relativity. It's pure geometry. And here is the mind-blowing part. The ER equals EPR idea proposes that these two things, the spooky quantum link and the geometric space-time tunnel, aren't just kinda related. It says they might be two different ways of looking at the exact same thing. The spooky connection is the wormhole. Get this, entanglement doesn't just happen in space-time. It might be the very stuff that builds space-time. Okay, I know, that is a gigantic leap. How could something as fragile and frankly bizarre as quantum entanglement build something as solid and stable as our reality? Well, a really powerful way to think about this comes from a totally different field, quantum computing. This is the key insight from a group of physicists in what they call the It from Qubit collaboration. They started asking a new question. What if the universe uses the same tricks as a quantum computer to keep itself stable? Just think about how a normal computer deals with mistakes. A stray cosmic ray can hit a chip and flip a single bit of data from a 0 to a 1, and that could cause chaos. So the classic solution is redundancy. You don't store a 0 as just 0, you store it as 0, 0, 0. That way, if one bit flips, the majority vote still tells you the answer was 0. The
The quantum version is like that, but on steroids. The idea is that a single piece of quantum information is smeared out, stored across a huge network of entangled particles. This massive web is incredibly tough to break, and the result? This super robust, error-corrected information projects as our stable three-dimensional spacetime.
Now, this isn't just some fun philosophical thought experiment. This whole idea has been put to the test, and it was used to solve one of the deepest, most stubborn paradoxes in all of physics.
So, way back in the 1970s, Stephen Hawking figured out that black holes aren't totally black. They slowly leak radiation and evaporate over time. But his math showed that this radiation was completely random, which meant that any information that fell into the black hole, like the information that made you, was just erased from the universe forever. This is a huge no-no in quantum mechanics, which says information can never, ever be destroyed. For almost 50 years, this paradox was a crisis. Then, in 2019, a physicist named Jeff Pennington, using these brand new tools from the IT from Qubit world, decided to do the calculation again.
So what did Hawking get wrong? Well, it was a totally reasonable assumption at the time. He treated spacetime as the fundamental background, as the stage. He had no idea that it might be the show itself, an emergent property built from a quantum error-correcting code.
Pennington's new calculation, the one that accounted for all this underlying entanglement, changed everything. He found that the entropy, which is just a measure of randomness, of that escaping radiation is actually really, really low. And that means it's not random at all. It's highly ordered, and it's carrying all the information of whatever fell into the black hole. So the information isn't lost. It gets out because it's encoded in that complex web of entanglement that's weaving space-time together. The paradox is solved, the fundamental laws of quantum mechanics are saved, and it's a huge, huge victory for this whole new way of thinking about reality. Okay, so is there any proof? This is where the story gets really fun, because scientists are now actively working on ways to figure out if this is all true. There are a few really cool approaches. You've got scientists trying to build tiny little holographic universes inside of quantum computers to see if space-time just emerges. You've got others looking up at the sky, searching for faint fingerprints of this ancient entanglement in the afterglow of the Big Bang. And some are even developing these incredibly sensitive detectors that might just be able to feel the quantum graininess of space-time itself. What's amazing is that an idea that was way out on the fringe just a few years ago has now been launched right into the mainstream. It's brought together experts from these totally different worlds, quantum computing and cosmology, who are now speaking the same language, all trying to decode the secrets of our universe. And that leaves us with one last, really deep question to think about. If the very fabric of our reality, space and time itself, is just a projection from a deeper quantum world, kind of a grand illusion, it makes you wonder, right? What other things that we take for granted might be illusions too?